Ben, we are back.
It's been a while.
Oh, it has been a while, but we've been doing it intentionally, right?
Yes.
So that we could get two versions at once, yes?
Yeah, it's called being efficient, and Rust is all about efficiency.
Exactly. Really, we've just embraced the idioms that is Rust. We've got some quick housekeeping notes before we start. As you may have noticed if you follow this podcast, there are now a bunch of This Week in Rust episodes also appearing alongside our voices, Ben. And this is really exciting. This is Nell Shamrell Harrington, who is the editor of This Week in Rust, who basically reached out and was like, hey, I have an idea for a podcast. Can you help me? And then we went, yeah, that's a great idea. You're going to be seeing a lot of those episodes going forward as well. We also have expanded the Discord for Rustacean Station. There's now also a category there for people who do other kind of media in the Rust world, in particular people who do Rust live streams, whether they're sort of coding or educational stuff. You can jump in there and find other people that produce other interesting Rust stuff if you're tired of listening to just Ben and I chat on like we sometimes do. But now I think we're ready to talk about Rust 144, Ben. What do you think?
That sounds great. And so I think it's actually perfect because 144 and 145 are both on the smaller side. So it makes sense to cover them both in one episode.
Yeah, I agree. I think it worked out exactly like we planned it.
But there are still some important things to go over in terms of like interesting digressions, as I think we are accustomed to around here.
Particularly prone to, it's true.
Yes.
The first one is the cargo tree got integrated into cargo. Do you want to explain a little bit what cargo tree is?
I actually don't know what it is. I didn't hear about this.
Oh, fantastic. Then I can explain what it is. So cargo tree is a command that I've been using a lot, actually. So cargo tree used to be this separate plugin you could install for cargo, where if you ran it, it would print a little tree of all your transitive dependencies and what version they were at. And it would also let you do inverse trees. So you could say, show me all of the things in my dependencies that depend on, say, Tokyo. And it would show you all the things in your dependency tree that depends on Tokyo. This is just a really nice way to like explore your dependencies, try to figure out how many you have, whether some of them might be like outdated or old, whether you're accidentally pulling in lots of crates you weren't expecting. And now this whole toolchain has been integrated into cargo. So starting with 144, you can now just run cargo tree and you'll see this like pretty output of your dependency tree that you can then do various interesting sort of introspections on to try to figure out what's going on.
Now to clarify, over the years, I have used a few different sort of tools for this purpose. Is this the one that prints out a graphviz file?
No, it prints it in the terminal. I did not know there was one that printed a
this one gives you like
file.
A nice like a graphviz file, which is like for a very large dependency graph is sometimes both overwhelming but also useful.
Oh, that's really cool.
Yeah.
The one I really hope gets integrated is cargo outdated, which I use just constantly. You can use cargo tree a little bit like this. In fact, one of the really helpful ways I've been using cargo tree is sometimes I find that my crate basically ends up pulling in two versions of some downstream crate, like 0.2 and 0.3 or whatever, like two major versions. And cargo tree is a really useful way to try to visualize why is it pulling in both. Because I can tell it like list all the things in my dependencies that pull in I don't know, like rand 0.6. And then it will just show you, here are the ones that depend on rand 0.6 below you. So it's a really handy tool for just understanding your dependencies better.
And then if you also go on to act on that and try and say like, hey, to your upstream dependencies, like, hey, you have this out of date thing, let me like update this for you. That helps the entire ecosystem to avoid the same problem. So it's a nice little public service if you choose to go that route.
Yeah, I've had some pretty fascinating, like deep explorations there where I go, okay, I need to update crate A, but crate A depends on crate B, so I need to update crate B, but crate B depends on crate C. And so in the end, I've like submitted 5 pull requests that are all just like bringing things up to date one by one. This is really handy if you're part of like the Hacktoberfest, for example. Works out very nicely if you just want to do lots of small contributions that actually end up helping the ecosystem. The other thing that landed in 144 was you can use async await now in no-stud context as well. This is really cool, but there's also some interesting stuff going on under the hood for why this is now possible and what mechanism is there that makes this possible. Do you want to speak a little bit to why this is interesting in the first place?
Sure. I think first, let's briefly just like quickly go over no-stood. For those who don't know, is a kind of profile that you can use with Rust that is intended for embedded devices, or I'm not sure what the correct term of art for it is, like low memory devices, like low power devices, like low capability devices. Imagine kind of like an incredibly simple, like just like microcontroller that you can like stick on the wall of like a factory, say, and have it run on like a very small battery for months or years at a time. It's a very different sort of programming than you would use for, say, making a desktop app or any kind of server application. And C is often used for this purpose, and Rust is able to also do this sort of thing, because Rust wants to be able to be used as an alternative to C wherever possible, but it does impose some restrictions. And in particular, you lose a large portion of the standard library. But one of the interesting things about Rust is that Rust doesn't want you to ever lose any language features as a result of using no-stood mode. There are some languages out there that try to support this use case in terms of like wanting to be both like, have the high level niceties of like a nice vector abstraction that can be allocated, and also like low level stuff. And some languages also impose, like, if you go through this route with this like more limited profile, you also can't use, say, like exceptions or whatever, or any various like maybe closures you can't use. And Rust is very carefully designed actually to not have that happen.
Yeah, it's interesting because one of the places where no-stood comes up a lot is when you don't have an operating system. Like, you don't have things like threads, you don't have a file system, you don't have a networking stack. And so all of those things you're going to have to sort of do yourself.
And in Rust too, like, and you wouldn't, if you use no-stood, you wouldn't have any library support from the standard library for these things, but you would still have closures and the result type, and everything else would just still work. Even panics work in no-stood, and they're a bit different semantically. And the only exception to this case until now, for the past few months, that's been stable anyway, was async await. And the reason that it was unstable, or it didn't quite work just yet, was because of some implementation details about async await and how it works under the hood. And we may have spoken about this back when async await was first stabilized, but it's worth reiterating. Async await is implemented in the Rust compiler by an abstraction called generators. And you may have heard that term from other languages like Python. The idea being that a generator is like a function. If you know a function, you've already got a handle on what a generator is. A generator is a function. Normally a function would run, you start, and it runs to completion, and you get a thing back. A generator is a function that you can kind of pause in the middle, get a thing back, and then resume again. And it's very useful to, say, model an async await sort of style as a function that has a loop in the middle, and after each loop you pause and then resume at the beginning of the loop over and over and over again. And it's useful to be able to do this. There are various enhancements that would make it even more useful. For the moment, the only way to use generator in Rust is through async await. Generators are not exposed stably to any kind of like, to any stable code. And one of the future enhancements is the idea of passing in arguments to the generator on each like resume step. But there are some there are some syntactic questions, there are some semantic questions, implementation questions. And in this case, the idea was internally, the Rust compiler was passing in arguments to each new iteration of the generator as it resumed, but there wasn't really any way to do it on the MVP that shipped last year without using task local storage. And task local storage is something that is generally provided by the operating system. I mean, I guess let's say thread local storage, really.
Yeah, it's thread local storage, yeah.
Thread local storage. So if you were no-stood, just no luck. But thanks to some heroic efforts to basically add the support for actually passing in proper arguments to generators, now you can use these in no-stood contexts. And like, I'm not sure. So do you have any examples of like what sort of thing a no-stood application might want to use async await for, John?
Well, so async await is an interesting model for embedded devices because you often don't have threading, right? You might just have one core and you're not implementing multi-threading because it's not like that's fairly complicated to implement and might even require special hardware that you don't have. And so the sort of like you have one event loop that manages everything in the system is actually a fairly attractive model on these platforms. And that's basically what async await gives you, right? You have the one executor that runs on the core, and it just keeps track of all of the asynchronous tasks that are either runnable or pending. And so it is really nice to be able to now use async await in that context, because it means that you can now write that sort of relatively straightforward asynchronous code, and then you could just run it with the executor that you implement for your embedded platform, rather than either having to like manually write all your futures or like implement full multi-threading, which is its own like huge task.
Yeah, I think it's fun to see the kind of things that we take for granted as, people who program generally for these more powerful machines, more capable devices with like OSs that give us all these nice things. And so generally, if you're like writing a normal app, you might even say, hey, I don't actually even care about using async await. I'll just use threads, which I'm used to. It is like, maybe conceptually a bit simpler, if a bit kind of more free-form and perhaps error-prone. But if you're writing for an embedded device, you often don't even have that choice. And so like this is kind of like you can now do thread-like things, asynchronous things, but in a single-threaded context. And
you can think of this basically as making it easier to write nice code on embedded platforms. That's basically what this enables. And it's interesting because the only thing that was really missing here was, as you say, the thread local storage, which is only needed for async await has, or futures in general in Rust. When you call poll on them, they require this context argument, and the context primarily includes the waker for that future. So the waker is the thing where when the future eventually goes to sleep, it yields, it says, I can't do any more work right now. Maybe there aren't any more bytes to read, or the buffer is full, or whatever. The waker is the thing that's going to mark that future as runnable again. Like if a packet comes in on the network or something, it's going to call wake on that future's waker, and now that future is going to be polled yet again by the main executor. And that context, that waker, was the thing that previously had to be stored in thread local storage, but that can now be passed through normal arguments through the work that went through this PR. There was another change that sort of was hidden a little bit deep down in the change logs, which is where we like to delve, and that is support for Unicode 13. And this got you a little excited, Ben. Can you talk about what this is and why it matters?
I want to clarify. I don't think that Unicode 13 specifically adds anything new, but I do think it's an important kind of thing to consider. I know that like when you come to Rust, say from like a language that doesn't impose Unicode, like Python 2 did not, C does not. Some languages do, but in a different way. Like Java and JavaScript impose different encoding, but they do use Unicode. But people usually just say, hey, like our language uses Unicode, but that's not quite as precise as you could be. Unicode is a standard and it has revisions all the time. To talk about what Unicode 13 is, like what does Unicode add? And people tend to think of Unicode as being like just a mapping, like, so this number mapped conceptually to this glyph. And then like Unicode doesn't take care of the font. Unicode doesn't take care of like any sort of thing about actually displaying the glyph. It's just a mapping. But that's not quite the case. Unicode has a lot of mappings, but also a lot of different rules about how languages should be treated and how different glyphs should interact. So to support things like vertical text or right to left text, or how different composing characters should interact. If Unicode were just a mapping of numbers to code points to glyphs in human language, that would actually be pretty easy, because you can imagine that adding new characters would never break old code in terms of as long as you weren't using this previously unregistered glyph or code points, it wouldn't be a problem. And that is the bulk of changes to Unicode in every revision are just adding things. I believe Unicode 13 added 4,000 or so different code points over 4 brand new scripts and 50 new emojis. And these are all things that are just strict additions, and they shouldn't ever have an impact on your code. But they do, I think, there are other things in there, like I mentioned, the different supports for scripts that go right to left or top to bottom, that sort of thing. Certain things can sometimes change, either because there was an error or in the previous specification, or just, things have changed, because human language is sort of a global mutable value, and you can't ever just sit in your heels and think about, hey, we're done. things will change and will be added.
It's funny because in some sense, like, language is like an additional version dependency that you have that's sort of unstated.
Yeah, and I do want to. I think we're gonna let's break the timeline a bit. I want to talk about quickly because it makes sense here. A feature from the next Rust release, 1.45, which
how
is that
convenient that we're also talking about that version
that
in this.
You and I had the foresight to discuss these two versions in this one episode.
Exactly.
But yes, there is a new feature in the next Rust version, 1.45, which is I say next, it's been released for weeks now, which now allows you to query the standard library and ask, hey, what version of Unicode do you support? Because if you wanted to be like really robust about your Unicode handling, you would be like, hey, like, so you would keep in mind the things that change from version to version of Unicode, and then add in support in your program, in your Rust code, that might do things differently based on what version of Unicode the standard library currently supports. And the standard library will only ever support a single version at a time of Unicode. And the Unicode version, changing things in the Unicode version is exempt from the normal Rust stability guideline because Rust has no control over whatever Unicode does. And being on an old version of Unicode is liable to cause even more problems in the long run. So Rust just kind of has to like suck it up and be like, you know what? If something, and Unicode is generally pretty responsible about this, as any kind of large project is. They try not to break things without reason, but still, like, things might change. Even just bug fixes might change behavior. The standard char or char Unicode version constant now tells you the version of Unicode that you can expect the standard library to support.
Yeah, and I feel like Unicode is in a position where it's so widely used that they're probably very, very wary of making like backwards incompatible changes. It's probably mostly sort of bug fixes and additions would be my guess.
But it's also such a large and subtle specification that changing anything could cause anything to change. So really, the choice is either don't ever change anything or try and carefully change things, which hopefully won't break things.
That's true.
But you can't ever be sure.
Another cool change that sort of seems minor, but might have impact for some of you is that rustc now actually respects the codegen-units flag in incremental mode, which might not mean very much to you, but the basic idea here is that when Rust compiles your code, it generally compiles each crate separately. And each crate is compiled sort of like a unit, like it's compiled as a single thing. And it used to be back in the day that only one sort of almost one thread could compile any given crate at a time. Now that's changed a little bit since, where it was able to split the compilation of any given crate using what are called codegen-units. But this used to be disabled in incremental mode, which is what the compiler usually compiles your code with. This is the mode that makes it so that if you compile your crate and then you make a small change and then you compile it again, that compile is much faster than it was if you just compiled your crate from scratch. And one thing that landed in 144 was the ability for the compiler to, or the willingness for the compiler to use multiple threads to compile a single crate, even in that incremental mode. And what this means is that, at least in theory, if you were building relatively few crates, like let's say you don't have many dependencies, you're really just building your crate, you might see that build be significantly faster after 144, just because it uses more threads to compile that code now. So that's kind of neat.
I wanted to talk about some of the const work that's been going on.
Oh yeah, always.
Library. In this case, there's always in this release there's a few new const APIs, things like I think getting little endian to big endian conversions are now const capable for integers. So things that should be const are becoming const as the const machinery gets more mature. One thing in particular I wanted to highlight was vecs and vec constructors and how those work. And so, for example, you may be familiar with the vec macro, just like vec exclamation point and then square brackets for making a vec. And this is probably ubiquitous, I think, for people who construct vecs these days. One problem with that macro constructor, though, was always that under the hood, it was doing things like, pushing to a vec or hitting append on a vec. And the problem is that the normal vec : new constructor actually doesn't allocate, which is a fun thing about Rust, that often things which are empty won't allocate, or things that which allocate will totally not allocate until you actually need them to allocate. Vec can be a zero size type, I believe, right? Or am I wrong in thinking that?
It's not a zero size type. It still takes up a space on the stack. It's just that it doesn't allocate anything on the heap until you actually put anything into it.
That sounds right. But so actually, there's zero heap allocation for it's making an empty vec. And previously, this constructor for vec was made const, and so now you could actually have, like, say, a const value or a static of vec, and you initialize it with just vec new, and it would just work because there wouldn't need to be any actual allocation at compile time, which is kind of a weird concept. And so this would totally work. And now the macro constructor for vec, if you have it empty, just vec exclamation point open square bracket close square bracket, that now maps directly to vec new, so that now works in const contexts. Now let me change gear and propose a radical alternative. So I think people are used to, say, like in Rust, if you want to make a heap allocated string, you use there's a bunch of different ways you could do it. We had a long war about this back from Rust 1.0. What should be the idiomatic way of making a heap allocated string? And should we have the string literal and then call .toString? Should we call .into and just have it turn into a string based on type inference? And the one that won out was eventually string : from the string literal. The reason for that was kind of it best exemplifies the idea that a string and a str are different things in Rust, where, like we mentioned before, the no stood use case, where no feature of Rust should be unavailable to no stood users. And one of those features that needs to work is string literals. And so you can't just have a string literal make a string implicitly unless you want your no-stood users to get grumpy at you. In Rust, I'm sure many beginners get this, where it's like you have the string literal, but it's not a string in terms of like capital string
capital S
that
string
lives on the heap. You actually need to do a thing to make it a string, and to do that, the idiomatic way of doing that is string : from, which I'm sure some people will still dispute. Beside the point. The idea being that strings and vecs in Rust are they're related, they feel like, right? Where a string feels like just a vec containing a certain kind of type, right? Containing Unicode. But it was a bit different. There was no string macro for making a string. It's this constructor, string from. But the vec macro was different. And the reason for that was a bit complicated. There always did exist a vec from constructor, and you could give it a slice of an array, and it would make the vec for you. But there were problems with this, one being that the vec would be created using borrows into the slice, because a slice is borrowed, and there wasn't really a way of having just passing in an array literal, like an actual stack array to the vec. And the reason for that was a thing that we've possibly discussed before, which is that in the absence of the ability to have type-level numbers, also called const generics sometimes, in a broader context.
Yeah, I think we talked about these a little bit last time.
Right, or even before. There's some cool things happening there, but the idea being that there are certain things in the Rust standard library that are only implemented for arrays up to size 32, and that's always been kind of regarded as a hack, where it's like, well, people like to use arrays of any arbitrary size. Why don't we just implement it for all of them? The problem is that there are quite a few numbers in math,
yeah,
even
it's weird.
in computer math, which has fewer than infinite numbers, and it's just not feasible to try to implement the same function, even with macros writing macros, to have the same function defined, say, 4 billion times. So this is what you need const generics for. You need the ability to write a single function that then on demand says, oh, you're trying to call this function with an array of size 1,612? Okay, here's that implementation for you, without needing to actually generate 4 billion other implementations of that one function for each and every function you might want to write. Recently, with the work in const generics, we have been able to kind of start thinking about lifting this restriction. And so I think actually the support nowadays is in fact mature enough to support this. It's just the Rust library team doesn't want to actually expose this yet until they're absolutely sure that const is ready for prime time.
Yeah, or at least some
actually
subset of const that we're
Yeah, you mentioned before. Do you want to go over like the arbitrary restrictions that we have right now to keep const from being too
Yeah,
exposed?
it's kind of silly, but also kind of cool. So the idea is that internally, the compiler is allowed to use unstable features because it doesn't actually leak out into the application code. This is what allows the compiler to like implement new features and then start testing them out internally, even on stable, because the compiler is compiled with nightly. And this means that internally in the compiler, you have access to const generics. So you can easily write like an implementation of from t, like an array of t's of any length n for vec of t. You can write that implementation for any n using const generic in the compiler. But if you did, you're sort of leaking the fact to the world that you're using this feature and that this feature exists. And there are a couple of reasons why you don't want to do this, but the way they've come up with not leaking this value is that there's a trait in the standard library called at most 32, which is only implemented for arrays of length that is less than or equal to 32. And so what they have is they have this impl of from array for vec, but only where the array of that length implements that trait. And the only thing this trait does is limit what implementations that applies to. And so the moment that const generics are actually made stable, they can just remove that trait from the impl, and suddenly the implementation is now visible to the whole world for any n rather than just n's up to 32.
Yeah, and so as kind of a precursor to lifting that restriction, getting back to my point and the radical proposal I have, you can now call vec from with just an array, using an array literal, a stack allocated array. And I think this is a great sort of mirror to string from. And in fact, when it finally becomes stable for arrays of larger than 32, I suggest that maybe it should replace the vec macro, which again, highly radical and contentious decision.
Very radical of you.
Only because I think macros are a little bit kind of opaque to editors, and they kind of don't play super nicely with incremental compilation. And to be clear, none of these are really deal breakers for using the vec macro specifically, which is a pretty simple macro. But when has something ever being not a big deal stopped programmers from arguing about something?
Wait, just so saying. Isn't then the Galaxy Brain solution here to not even use string from, but use vec from and list the characters one by one?
Oh, we could do that. We could add an implementation of vec from, specifically using specialization, which is still unstable, for bytes, and then you can type vec from and then have a binary character literal before every single character.
Nice. It is interesting.
Yes, and then we can have, and then to make it nice, we have a macro called string.
Stringify.
Do that for you.
Stringify vec.
Perfect.
Is what it should be called. It's great. It is funny, actually, because I looked into this a while back, and it turns out that a string is not a vec of characters. And this turns out to be important in a bunch of ways. The char type in Rust is actually specifically a Unicode scalar. It is always 4 bytes long. It's like a 32-bit integer that represents a Unicode scalar. So it doesn't use UTF-8, for example, whereas a string is a UTF-8 string. So it's a UTF-8 encoding of that particular string in Unicode. And so if you have a vec of characters and you want to turn it into a string, you actually need to encode it. It's not just a straight transformation, which was interesting to me.
Getting back to Unicode being a bit more than just a mapping, it's a lot of things, and it also specifies behavior, which sometimes changes. Hopefully, not too much. Though.
Speaking of things that change, are you ready for this? We also got a change to Rust 145. Huh? How do you like that segue?
I'll give you partial credit for that segue. That's fine. That's fine, but yeah, I think we're done with 44. Let's move on to 45, which I don't have very much to talk about in this. Do you want to start?
Sure. I can kick us off with what's been like basically a very long journey that talks to a little bit of like interesting low-level interplay of Rust and LLVM, which is the compiler backend used by rustc. So this is an interesting weird quirk in Rust that's been standing for a long time. I think this issue first came up in 2013.
Let me even give you some more context. Ahead. This is the oldest unsoundness issue in the Rust code base. Also, until recently, it was the oldest open one by dint of also being the oldest one. And so the fact this dates to well before 1.0, and it should speak to how thorny this was to actually resolve in practice. Hundreds of comments, dozens and dozens of commenters over the span of 7 or more years.
and
trying to fix this
the funny
bug.
thing is the bug itself is fairly straightforward. It was what is the right fix that was the big debate. So the bug here is basically if you have a floating point number and you cast it using the ask keyword to an integer type that can't hold the value that's in the floating point number. So imagine you have the floating point number like 1024.2 and you try to cast that to a U8. Then there is no representation of that number in a U8 because a U8 can't hold values larger than 256, 255, I guess. And so what do? How do you convert this float into that number? Because that's what the user asked for. And here begins the discussion of what is the correct value to end up in that integer at the end. Do you want to talk a little bit about the debate?
Sure. I mean, so generally in Rust, whenever someone is faced with like, what should we do? The first answer to my mind is always, we probably aren't the first people to have this problem. Let's just see what other people have done. And so there are various schemes for other languages. I believe the scheme that we eventually settled on is just taken from, maybe Java does this in terms of like, do you like, if the number is too big, does it become infinity or does it become the maximum number? Or if you have like a NaN, where does it go? That sort of thing. And I believe we just took Java's. I'm not sure about the full like spectrum of like different languages doing things. Maybe Java also took from somewhere else, or maybe other languages have Java's semantics as well.
And what happened before you fixed it? Like before...
Well, so yeah, that's a good point. And so you mentioned like, so it is right. It is a nice intersection of, so kind of like Rust tries to not tie itself to any particular code gen backend. And so like, for example, recently, the past year or so or more, people have talked about like using a compiler called CraneLift as the backend for Rust. The idea being that you would compile Rust code and LLVM wouldn't even be involved in the slightest. And this is possible if you are very careful when you design the language to not have your behavior depend on any implementation details of the underlying backend, right? And so this takes a lot of effort and a lot of foresight and a lot of caution, but it can be done, with the idea being that, like, hey, you don't want Rust to be implementation defined for all eternity, and LLVM doesn't have like a specification, right? You can't just say, hey, look at the LLVM spec for what we do. It's kind of just, they do what they do, just like we currently do what we do. And so if you ever wanted to write, say, like a GCC backend for Rust, or like, there are other less complete backends, like the mrustc is a different kind of like, example backend, example reimplementation of the compiler doesn't use LLVM. It's all its own thing.
Yeah, I
believe
that's
anyway.
Right.
And then, CraneLift too, like there are good reasons to want to write a different backend. And so you want to be careful to not couple any user visible behavior to implementation details of your backend. This was one example where things did leak through kind of out of necessity, because obviously if one of the big things and one of the important features of a language at Rust's level is that you want to have support for doing math really, really fast. In some sense, computers are all about doing math really, really fast. And so the most basic things, like just doing operations on floating point numbers, need to be really, really fast. And so LLVM provides various like intrinsics, I believe is the terminology that LLVM uses. Rust uses that, but I believe they use it as well. And the idea being that whenever Rust says, hey, like, you want to add like this integer to this integer, well, we don't have like a routine for that ourselves. Why would we? LLVM has that. We'll just use that. And because LLVM can, like, based on the platform and various optimization settings, it can do the absolute fastest thing doing what LLVM does best, which is to make fast code.
Yeah, so it's attractive
and in this case,
do what LLVM does.
Yeah. You want to just do what LLVM does, as long as you can still guarantee that, the behavior is sane and does not couple you to really weird semantics. And in this case, they were using to convert from an integer to a floating point, or is it, I was getting confused.
Floating point to an integer.
Floating point to integer, other way around. They were just using an intrinsic provided by LLVM. And LLVM's behavior here is kind of based on what C says you can and can't do with numbers. And I don't want to talk too much about this because I haven't quite read up on what C does. I don't want to like betray my extreme ignorance here. But C is not as strict. I mean, like, it makes sense. C was written in the 70s. C is kind of like, advanced
and in the 70s,
it is designed to be extremely flexible and not over-constrain what an implementation.
Yeah, and in the 70s, everything was allowed.
Yeah, and so it was like, it's totally reasonable. And so nowadays, the things that you think are... C predates floating point numbers as a spec. Like, IEEE 754 is, like, way after C. It's like... You think about like, all these like Unicode, like UTF-8 comes after Java, after JavaScript, all these things. Like these languages like have been around for a while. They are venerable. And so things you take for granted just weren't around back then. C doesn't really prescribe what you must do in these cases. And so LLVM is like, yeah, we do it. We're mostly, we were originally conceived as a C compiler. We'll just by default do what C does. And it turns out undefined behavior is often what is allowed in these cases. And so the debate for many, many years is like, well, do we add checks ourselves for these cases? Will that slow things down? And they tried, they benchmarked, and the answer is yes. And so I believe it just took a long time of figuring out how to add in checks in like what you want to do, first of all, and then how to add in the checks in a way that minimizes the performance cost.
And it was...
And then ultimately...
And it was important that it wasn't undefined behavior too, right? Because casting a floating point number to an integer type isn't unsafe. But the idea is that safe code should never trigger undefined behavior. And this was an exception to that. So there had to be like a well-defined answer to this that was safe, that did not introduce undefined behavior.
Right, and so in this case too, good thing you mentioned that, because now let's time travel back to 1.44. Two of the otherwise overlooked APIs are to int unchecked for F32 and F64, and these essentially just give you the old behavior, right? Where it's like, you're using these intrinsics, maybe because like maybe you've benchmarked with this new change, which came about automatically in 45, and you said, hey, like, actually, I need to be fast here, and I'm being careful. My data doesn't contain any nans or numbers that are too big. I just want the old fast behavior, the straight-through intrinsic. Give me this unsafe method. And that's what that's for, essentially. And so the idea being that there shouldn't be any major performance cost. I think like it was only a few percent in any benchmarks.
A few percent? That's outrageous.
But still, for some people, that's
outrageous. How can you steal a few percent?
I mean, I don't know. I mean, like... different people have different benchmarks. You never know. Someone might really matter. I mean, like, I don't do any like graphics programming, which I imagine. I'm trying to think, even like rack my brain, like in what context would you even want to like convert floating point to integer? It's kind of weird to even think about. True. But like for me, I'm sure someone out there is yelling at me, being like, "No, I do that every day," and I'm sure you're right. I just don't know it. I assume it's something to do with graphics programming, where you're like you have like this like strange fluid like 3-dimensional space, and you want to convert it to actual coordinates in a reasonable way. That's probably what you're doing. Or like simulations where you'd be doing the same. So I can imagine that for those people, they want to use these methods if they have benchmarked the problem. But maybe it's not a problem.
Now those methods are rightfully unsafe.
And also the problem is fixed, and so it is a victory for Rust closing extremely old and thorny unsound issues and not throwing up its hands. I mean, I remember back in the day, like literally before Rust 1.0, I remember like some people just saying, this is never going to be fixed. This is just like, people won't accept any sort of slowdown here. I don't see what we could even do here. And I'm like, no, we must do it eventually. It's important for, like, you can't say Rust's idea is it compiles, if it compiles but unsafe, it's totally safe, modulo bugs. Yeah. This is a bug. This was a bug, and then now it's fixed.
I wonder what the now oldest bug is. Like soundness bug.
I mean, I can look it up. I mean, GitHub has a nice interface if you want to go over the next thing while I look this up.
So the other cool thing that landed in 145 is something I've wanted for a really long time, which is function-like procedural macros in expressions, patterns, and statements. And this that's a little bit of a mouthful, but the basic idea is that if you have a declarative macro, like you write macro rules and then the name of a macro and you define it directly in your code, then you can call that macro in like basically anywhere. You can put it in in expression context, for example. Like I can say let x equals and then my macro. And this is how you use the vec macro, for example. It's usually used in expression context. But it used to be that you couldn't do this for procedural macros. What this meant was you basically couldn't write the vec macro, for example, as a procedural macro. If you did, you wouldn't be able to call it in like let x equals my vec exclamation mark. It just would not compile. Now, there was a pretty well-established workaround for this. There was a crate called Proc Macro Hack by David Tolnay that works really well. It basically lets you do this, but it was definitely like a hack. It was a workaround. And now, finally, in 145, this just works the way that you would expect it to. If you now write your own procedural macro, that macro can be invoked in expression context, but also can also be invoked in a number of other contexts that were previously unavailable. So for example, you can now use your procedural macro in pattern context. So you can use it with like an if let or a match. You can use it in statement context. So you can use it as like this thing and then semicolon in the list of Rust statements, which was also previously not possible. And one reason why this is really cool, beyond just making things that should work, is that this was the last thing that was holding back the Rocket web framework from working on stable. And so now, finally, with this final feature implemented, you can now use Rocket on stable without having to enable any features. And so this is definitely like a huge win in terms of both the ecosystem, but also just in terms of not being surprising to macro authors. Like I know I certainly ran into this the first couple of times I tried to write procedural macros myself.
Oh, I was actually looking at this unsoundness stuff.
Did you find the issue?
Oh, I did. Yes, actually. So, I mean, currently, it's very silly. It's if you cast to a trait object of any, you can then get a type ID, which according to the docs is a globally unique identifier. But because of some weaknesses in the hashing algorithm, it's possible to find birthday attacks.
Oh, that's
potentially
so stupid.
To find collisions among these globally unique identifiers. Yeah, that's not. It's listed as priority low. So it's kind of extremely silly, but it is. We gotta fix it, and there are ways to fix it. It's kind of no one's priority right now, so it'll get fixed someday. But yeah, that's the current oldest thing.
There are a couple of smaller changes in 145 that I think are also worth talking about, and one that I ran into recently and only discovered landed in 145 because I tried to compile in 144 and it failed, was the ability to use the character type with ranges. So for the longest time, you've been able to say like for I in 0 to 100 using the ... or ... equal syntax. And now you can do that with character ranges as well. So you can do things like for C in A ... equals Z, and it will iterate over all the characters between A and Z. And this actually works for basically arbitrary Unicode code points, which is pretty cool. So you can iterate over things like emojis if you wanted to, although you'd want to get the order right so it's not like a weird kind of loop or it just panics. But it is kind of cool that it's now possible to iterate over ranges of Unicode code points. It's just like a neat addition to me.
I think that's all I have for 1.45. And so is that all you have as well?
I have one more actually, which is and this is something that like has annoyed me so much in the past, which is imagine that you have a string and it has some prefix or some suffix that you want to get rid of. Well, it used to be that there was trim matches start and trim matches end, which would remove a given sort of pattern from the start or the end of your string, but it would do so repeatedly. So the idea is that you use trim for things like white space, where you want to remove any occurrence of white space, no matter how many there are. But if you want to remove like a string prefix, then you kind of only want to remove it once, because it could be that like there's like imagine there's a separator like a comma or something, or a double quote. If the thing inside contains one of those, you don't want to strip that as well, even if it comes at the beginning. And now finally, the stir type has a strip prefix and strip suffix methods that basically remove a single occurrence of the input from the start or the end. This is something that it just saves you writing that function yourself, and it's really nice. And then I think there was one small cargo change that's worth mentioning. This is also a minor one. Like there's a lot There are lots of fixes in cargo in 145, but none that are particularly large. But one thing that you might notice is in the past, cargo was not great at telling you which files there were errors with. Like, for example, if you tried to compile a file that you didn't have read permissions to, cargo would just sort of fail with access denied and wouldn't tell you which file it failed on. And that has finally now been fixed. Like, now you will actually get the file system context for the various file system errors you get, which is a really nice addition. That, I think, is everything I had for 145.
Okay, there we go. And I believe you also had some follow-up remarks for
so this is
well.
a small point, but one thing that might be interesting to you, if you find these podcasts interesting, if you find the This Week in Rust podcast interesting, is that there's a decent amount of content out there for Rust now, and especially from things like the core team. The core team of Rust recently announced that all of their agendas are now available completely in public. That includes things like the sort of agendas and I think even the transcripts from their meetings. And this is a great way to just keep up with what things are important to the Rust core team at the moment. So I recommend you give that a look if you're interested. And I think that's all I have.
And we'll link to that in the show notes. And yeah, that's all that I have, all that you have.
Great.
All that we have.
I guess I will see you again in 1 or 2 releases.
I kind of like this cadence, but I think it'll depend on how big each release is. And so I think now that we have the This Week in Rust to kind of fill out the roster, I'd say let's reserve this for every other by default, unless there was a really big, like async await would have deserved its own release. But other than that,
I think it works pretty well. Well, so long, farewell.
All right,
Auf Wiedersehen, goodbye, as they say.
Yeah, sure. They say in Spain.
All right, see you, Ben.
So,
bye.
Farewell.